Okay, so this is, again, a very short summary. We just should kind of wrap up a little bit what we've done, but on a very, very short, whatever, 10 minutes from now on. So what you should have learned in the course or things, if you don't know anything, if you don't know one of the things I'm talking here about today, that means you should really, really revisit the course material. Although knowing only what's in here is definitely not sufficient because it's a very high-level overview. So what is SLAM? We define SLAM in the beginning as we want to estimate the trajectory of the robot or the path that the robot took or the sensor took doing data acquisition, as well as the map of an environment, of our environment. So the path and the map, given my sensor observations and given the controls that the platform actually executed. And we've learned different variants, what a map could look like. It could be a set of landmarks, 3D poses in the environment. It can be a dense grid map. So we looked at different aspects on how we can actually represent the world, and this in combination with the trajectory of the robot, which can be in 1D, can be a 3D, can be in 6 degrees of freedom. It just depends on the platform that we're using and the assumption that we do. We're interested in a distribution, so in a probability distribution, because typically the best match is not always the best match. So we're interested in the probability distribution given our observations and given our controls. So we want to exploit that. And SLAM is often referred to as kind of a chicken or egg problem, because if we know the poses, estimating the map is easy. And if we know the map, estimating the poses is easy, because one is kind of just mapping with known poses, and the other one is just kind of localization, which are in itself easier problems than solving the full SLAM problem. If both quantities are unknown, it's actually more difficult to do that. So we mainly looked into 3 paradigms and should be aware of all the 3 paradigms with all its advantages and disadvantages. The first thing was the Kalman filter and its friends. So it was the Kalman filter, was the extended Kalman filter, was the unscented Kalman filter, was the sparse extended information filter, was the extended information filter, although the extended information filter we touched only very, very briefly. And then we looked into particle filter applications. So how can we solve the SLAM problem with the particle filter? And there were mainly the FastSLAM approach for landmarks and kind of the grid-based variant of FastSLAM, or this was called grid-based raw black-blast particle filter for mapping, which are kind of the 2 of the prominent solutions out of this particle filter group of approaches, which have been used to address the SLAM problem in a couple of different systems. And finally, last but definitely not least, the graph-based approaches, which we present in the end, which is motivated by reducing the sum of the squared errors, which can be shown to be equivalent to finding the mode of my Gaussian distribution. And there are some nice advantages of the graph-based framework in terms of the flexibility that it gives you in terms of linearization or relinearization, so that the graph-based approaches are the most frequently or the most popular used ones, at least from the, let's say, more modern systems proposed after 2006, perhaps. Before that, Kalman filter was kind of the dominant system which was used, but the graph-based approaches is a system that is very, very frequently used in the context of SLAM. We typically distinguish 2 different variants of SLAM. This one was full SLAM, where we estimate the whole trajectory of the platform and the map of the environment, compared to the online SLAM problem, where we said we're only interested in the current or the last pose of the robot. Of course, we're not interested in the previous poses, so we marginalize out the previous poses, and we're only interested in the map and the last pose that we have. So in the graph-based approach, we always estimated this full trajectory. In the Kalman filter-based approach, we typically stick with this one because we only had the current pose of the robot in our state vector. So what you should have learned in that course, shouldn't have idea what the SLAM problem is. That's, I think, hopefully the case for everyone here. You should know how to build a landmark map of landmarks and also grid maps. So if I at least give you known poses and a data set with observations, you should be able to generate a nice looking grid map and a nice looking landmark based map. So it's just mapping with known poses. It was kind of the very elementary part. And then we looked, or then it was kind of a different order. Chronologically, we started with the EKF framework. You should have a pretty good idea what the EKF does, because the EKF is kind of The first successful system which was used in SLAM, a lot of systems, especially older systems, still use the EKF framework. It's very widely used, and kind of understanding what the particle filter does, which assumption it does, what its limitations are, is kind of a really, really important part of understanding. Also the motivation for a lot of approaches that have been presented afterwards, because there's a huge number of papers just trying to find solutions to what the problem that the EKF has. Then we looked into the sparse extended information filter, so you should get an idea what was the key advantage, why did we move from the EKF to the sparse extended information filter. The constant time algorithm or nearly constant time algorithm, which was a huge gain compared to a quadratic complexity that the Kalman filter has per iteration for our large, for n landmarks, because we have to maintain the full matrix over here. Then we looked into the particle filter-based approaches, so you should know what a particle filter is. You should get the idea of the particle filter at 3 key steps. So drawing samples from the proposal, computing the weight, and the resampling step should be things that you are aware of and you know which things are exploited in order to apply that to the SLAM problem. What was the Raub equalization? So how do we split up the estimate about the trajectory of the robot from the map of the environment in order to do that efficiently? That was kind of the key ingredient to make the particle filter work in the context of SLAM. And then we looked into the graph-based approaches, which we just did after the Christmas break here, and discussed kind of the key elements, how to build maps, how to do it with landmarks, how to deal with outliers, how to arrange them in a hierarchical fashion to become faster. And we also very briefly looked into front ends. The other thing that I hope that you learned is some hands-on experience. At least if you have followed the exercises that Rainer and Fabrizio did here during the term, you should have the ability to code a standard SLAM system. Definitely the backend. Actually, you should be able to do code an EKF, you should be able to code a particle filter, and you should be able to code a graph-based SLAM system. At least if you have done the exercises, you should have experienced the, let's say, at least key aspects of those systems. Of course, there was a framework given to make your life easier, but really my hope is if you sit down and say you want to try something and you want to, let's say, you have a good idea and you want to modify the graph-based SLAM system to get this nice idea, and you should be able to implement that. That was actually one of the targets that I set for myself to that course. And the next thing, which we haven't tried yet, is actually understand a typical or average SLAM paper from a conference. If you look to any large robotics conference, you will see several tracks, so it means they have several sessions. It means multiple authors put together talking only about SLAM. You have multiple sessions of those. So there are a couple of SLAM papers you find in any large conference, and my goal is that you actually understand most of them. Definitely not all of them. I also don't understand all of them. But there should be a really large number of papers that you understand. Or at least you get 90% of the paper. Maybe some comment here, some comment there. It's always the case that you may not understand that, or one doesn't understand that, including myself, of course. But you really should be able to get the key idea, what do the authors want to communicate. And therefore, a lot of the course material which is on the website are actually papers on which I reported here, and you should be able to understand basically all of them which are on the website. That was at least my goal. So if you want to continue working in this context, in the context of SLAM, you should be actually well prepared to do that, because you know what has been presented. So even presented approaches here in the course which have been developed last year, have been published last year. So a lot of up-to-date material in there, and I try to actually give you a good overview on what happened here. So a comparison of the different approaches. So I'm not a really big fan of saying, oh, this one is much better than the other one, because it always strongly depends on the application that you're using, on the assumption that you make on your platform, on the whatever, which way can you engineer your environment, if you can bring out the perfect features in the environment because it helps the application. There's no reason to not do that. But at least kind of a little bit of a comparison on what different systems can do. I would like to do here, and I would like to do that together with you on the blackboard, because then you probably remember it better. So we had the Kalman filter approach, we had the EKF, we had SIFE, we had the particle filter, and we had the graph-based approaches. Or let's say Gaussian, whatever. And then we have here computational complexity. We have the assumptions about the distribution. These are kind of obvious terms. Then what about the linearization? Is this problematic or not? In terms of flexibility, so how flexible is this system actually? Flexibility. So how easy can I, let's say, change a constraint if I later on realize, oh, I made a mistake in the beginning. I can actually get rid of this constraint or fix things. And how well are those systems for large-scale SLAM? Large-scale SLAM. Okay. I would like to discuss this with you now. What was the computational complexity of EKF per iteration? N are the number of landmarks. What was the complexity to deal with?
N3?
No. N3, in general, I agree with, but not for the SLAM problem. Because the issue was we need to do an inversion, which is complexity of 2 to the power of 4 approximately, which is part of a cubic complexity class, but the issue is we need that only if we can, our observations allow us to observe all features at the same point in time, which doesn't hold for large-scale problems because we're limited sensor range. Okay, let's say we have n landmarks. How many operations do I need? In the worst case, per iteration. Okay, I have a quadratic complexity. I have my covariance matrix, which I need to represent, and I do all the operation with the covariance matrix. So we typically end up with a quadratic complexity. What is the assumed distribution of the Kalman filter? What kind of distributions can it represent? Yeah, perfect, at least. So purely Gaussian. What about linearization or linearity assumptions? Yeah, everything, all linear. So it's not even linearization, it assumes everything is linear, and if it's not linear, it can't be applied. How would you rate in terms of flexibility? How flexible is such a system? How easily can you change things? It's a weak measure, so you can just communicate what you think a little bit. Sorry? Not that flexible, I would agree with that. In which area would see some flexibility if it's not too flexible? I mean, there's some flexibility in there. Where would you see that? Anyone else?
It's good for feature-based map or landmark-based map, more than grid map.
This is definitely a statement, so it's more designed for the landmark case where you estimate the position of the landmark. In terms of flexibility, one of the things that it also allows you to nicely encapsulate the front end from the back end, because you only get a Gaussian estimate in there. So whatever your sensor is, as long as your sensor gets out a Gaussian, you can fit it in there without needing to change your back end, which is actually kind of nice. So I give it a medium flexibility. It's kind of, what about large-scale mapping? Sorry?
It's not good for a large scale.
Why?
Because it's too complex.
Yeah, so that's more on the minus side. That's kind of, doesn't really scale. Okay, let's go to the EKF. What happens with the EKF? Exactly the same as done as was here. What about the assumed distribution? Again, Gaussian distribution, yes. What about linearization? Do we linearize in the EKF? How can we deal with nonlinear functions in the EKF?
Yes.
Yes, in which way? Exactly, by linearization, how often do we linearize? How often do we linearize? Yes, that's true, but so every function is linearized only once. So when we get the observation, we once linearize, and then we stick with this linearization point forever, because we integrate into the system. So we linearize once. So if you are far away from a good solution, that linearization point may not be good. In terms of flexibility,
Higher than KF.
sorry?
It's higher than KF.
Yeah, I could give it simply the same score, of course. The linearization helps us a little bit, but it's not dramatically different. In terms of large scale, we have exactly the same issues as with the Kalman filter. Same complexity. Okay, let's go to the sparse extended information filter. What was the complexity of the sparse extended information filter in terms of number of landmarks?
Constant.
Yes, constant. So that's really cool. Constant time. It's a big win. What in terms of the underlying distributions that I used?
Gaussian.
Yes, again, Gauss. Linearization. Exactly, it's exactly the same with the EKF. Once. Flexibility.
A little bit higher than EKF.
Why?
A little bit higher than
Why?
Because it's easier than.
It's easier. It's really easier to implement and easier to use. You'll be the first one who says that.
Hard to implement, but it's more flexible.
Oh, in which way? What you can do with what you can't do with EKF?
No, because you have to consider how to sparse your matrix. That's why it's harder to implement.
Yes, but I mean, in terms of flexibility, I just want to go back to your flexibility statement. Why is it more flexible than the EKF?
Because it's constant complexity.
Does it make it more flexible? It's faster. I completely agree with that. And so I would even give it a very similar score than the EKF. So I wouldn't change that too much. In terms of large scale mapping,
Yes.
yes, it's really good because it's a constant time algorithm. Whatever time number of landmarks I have, it takes the same amount of time. That's a really big plus. It has a certain minus, so why it's not the absolute super brilliant thing is, it still suffers from the fact that you linearize only once. And if you add more and more nodes and the thing becomes non-linear, you're likely to diverge as well because the linearization assumption doesn't hold. So if you go to really large scale maps, there's a limiting factor which results from the fact that you linearize only once. Okay, let's look to the particle filter. Let's do only landmarks here because let's say, or what is the complexity of the particle filter? If you do the right implementation, not the trivial one. So we're talking about a computational complexity, not memory complexity. So it was linear in the number of particles and logarithmic in the number of landmarks. Because you need just to go to this special tree structure, which you can do in an efficient way. What are the assumptions about the underlying distribution? So exactly, so I don't make any assumption unless that I can represent it with particles. For the pose any. For the landmark given the poses, I assume to be Gaussian. Landmark given poses was Gauss, at least in the for the FASLAM. What about linearization?
Use sampling instead of linearization.
I typically don't linearize in there because I can just have the propagated points, so I don't need the linearization. So not needed. At least for the poses. For the observations, it may be different. This depends on my implementation. In terms of flexibility, why?
Because we can use any kind of distribution.
That gives me gain flexibility. I agree. What else?
Something, because of the sampling.
Yes, assembling is also nice. What else?
We don't need to linearize.
What else? What is this thing I can do better than I couldn't do before?
We can multi-different hypotheses.
Exactly. So we have multiple data association hypotheses. So I don't need to necessarily commit on one data association hypothesis. I'm really flexible with respect to the data association, so that gives me a really nice plus in terms of flexibility. What about large scale? Yeah. So log n is still pretty good. I mean, constant is better, but it's still pretty good, and it has some of the advantages with the linearization, with the linearizing ones. That's better here. So what's the complexity of an iteration of my graph-based approach? Everything sparse, all is good. So I build up my H matrix. Well, what do I iterate? It's always a sum in there. For H, for B. It's linear in the number of edges. So I have to iterate over all edges because these are the things I need to accumulate in my matrix. And under the assumption that everything is sparse, which is the case if I don't observe the whole world with my scanner, it's actually linear in the number of edges. It's called edges, which somehow scales with the number of positions where the robot has been, because I typically have constraints between them. Of course, I may revisit the place, I may add some more, but in most of the cases is some function of the number of nodes to some degree. And of course, I need to iterate, but typically, if I assume I iterate a little bit in every point in time, that's just a constant factor. I do, let's say, n operations every time I add a constraint. Right? It's roughly linear in the number of edges. What about the underlying distribution? What's the assumed distribution?
Gaussian.
Yes, Gauss, but no. What did we add to that framework to leave the Gaussian world? We were able to deal with outliers. Plus outliers. There's an important point for robustness. We need to be able to deal with outliers. So if a few constraints are really completely off, we have really good ways for dealing with that. Linearization. What about linearization in here?
Like column filter.
Sorry?
Linearize once. No?
Don't make me cry. It was one of the key advantages that every time we take our cost function, we linearize it. Computer solutions, at every iteration we relinearize. Relinearization. And this is a big plus because even when we started with a bad solution, as we relinearize, in every iteration, the closer we get to the hopefully right solution, the better the linearization gets. And that's one of the key big advantages if you deal with somewhat nonlinear systems. It's really an important point, which increases robustness, especially for large-scale mapping for the graph-based approaches dramatically. What in terms of flexibility?
It's really flexible because of different front ends.
Yeah, it gets 2 pluses from my side because you can add constraints, you can have multimodal hypotheses you can take into account with the max mixture approach. You can remove stuff. Of course, the thing grows with the trajectory, so that may be slightly bad, depending. But there are even ways for kind of bringing that down. You can optimize it a little bit to throw away some of the information that's collected. So that's really flexible. What about large-scale mapping?
Plus.
Why?
Because you did it in the showed in the video.
Yeah. So actually, I would even say it's -2++. It depends on what you're actually using. If you do non-sparse, full stuff all the time, it could even be a minus. But if you use these hierarchical approaches and really invest some time in how to solve the problem in an efficient way, you can actually do that in a very efficient manner. And so you can argue if these are 2+ or 1+, but this is just a rough indication of what is these things typically look like. Okay. I'm more or less done. The timer's over, I know that. I'd just like to know, where do you see open issues? Everything solved? What are open issues? Where do you see open issues?
Better way of optimization of graphs then.
Yeah, although you argue the system works actually quite well, that you, for practical solution, that works quite well. So it's not the graph optimization is actually not the bottleneck anymore. I think we can confidently make this statement for most systems, at least. I mean, you could see it from a general point of view, not about just this optimization, but in general, Flam. Can we do everything? Okay, you guys are too tired. So just listen to a few of them. So some of the things which are still open issues are dynamic environments. What if the environment changes? So far, we always made the assumption the environment is static. So especially systematically changing environments. If you're, let's say, in a factory and in the morning, typically the world is in state A, later in state B, later in state C, there's a systematics, or there's systematics in there and how to actually exploit that. Seasonal changes, if you're outdoors, drive around with your camera, a nice winter scene at Schauinsland looks dramatically different than in summer. And it would be nice to actually recognize this if you want to do SLAM across multiple seasons. Online solutions is also something which is, yeah, there are ways there are quite some good online solutions, but if you scale that to larger and larger and larger environments, at some point in time you may still can't optimize it every point in time. Lifetime operation is related to the previous things, is something which still is not fully solved, and how to efficiently also find constraints in there, because if you have a lot of observations, finding constraints even becomes a big bottleneck. Resource constraint system, if you do everything on a small helicopter which has whatever, the computational power of your mobile phone, and you want to do everything on the mobile phone. People are working on that. There have been dramatic progress in this respect, but they are still not the out-of-the-box solution you can buy. It may come up, but currently it's not available. And especially on resource constraint systems, like whatever, flying vehicles, humanoids, there's still limitations on what you can do on those systems. What about failure recovery, or if you're going to go for zero user intervention, the system should identify itself if it made a mistake. Also something which is not really solved yet. And also the question of how can we exploit prior information? So given we have some knowledge about what the world looks like or typically looks like, can we actually exploit that to build better maps and kind of not start everything from scratch with robot is completely, the hard disk is empty, it starts from scratch. What can we do in order to exploit what other robots has learned, sharing maps between robots, or relying on previous knowledge that other systems accumulated or the system itself has accumulated beforehand? Can we exploit all that information to actually build better maps? That's something which is also still somewhat an open issue. Okay, at that point in time, I would like to close this course. I would just say it was, again, a big, big pleasure to teach this course. You will be the last course, actually was teach this course, at least here in Freiburg from my side, as I'm going to leave Freiburg University basically day after tomorrow or something like that, and only will come back for the exams. But I have to say it was a great pleasure with you guys. Maybe someone else is teaching it next year, I don't know. But I really enjoyed it. It was a nice course, also enjoyed the interaction with you. So thanks again, and maybe we see each other in the future somewhere on a robotics conference or something like that. That would be a nice pleasure. Thank you very much.
Thank you.